The other type of flow in a hemodynamic system is turbulent flow. And by definition, turbulent flow is non-layered flow. In other words, if you disrupt the layers in a laminar flow system, you end up with turbulent flow. Now, the most important characteristic of turbulent flow is that it is noisy flow. It creates murmurs. So if you're putting a stethoscope up to a vessel and you hear something, what you're actually hearing is the turbulent flow. Now, another characteristic, which is not nearly as important for step one, is that turbulent flow increases the resistance of the system. So if you move from laminar flow to turbulent flow, then it is more difficult to pump that blood through that hemodynamic system. Now, it is possible to calculate a number that will tend to predict whether you have laminar flow or turbulent flow. Now, that number you calculate is called Reynolds number. Now, they're not going to test Reynolds number on the exam, but they may test your understanding of the parameters or the variables that contribute towards Reynolds number. So on the next page here, then you should understand the important variables that promote turbulence. First of all, increasing tube diameter will promote turbulence. All we're saying here is the larger the diameter of the tube, you're more likely to get turbulent flow. So turbulent flow is more likely to occur in large diameter vessels than in small diameter vessels. The second characteristic that tends to promote turbulence is increasing velocity. Now, don't forget, this is speed. If you increase the speed through the hemodynamic system, you're more likely to disrupt the layers and get turbulent flow. Now, finally, as part of Reynolds number, then, if you decrease blood viscosity, that is, developing anemia, that also promotes turbulence. So if an individual slowly develops anemia, the decrease in viscosity will tend to turn laminar flow into turbulent flow. Now, there's a couple of other variables that will also promote turbulence, but they're not part of Reynolds number. One is branching. If a single vessel branches into two vessels, that branch point will promote turbulence. It disrupts the layers when you go from a single vessel to two vessels. Now, a good question for step one would be the following. The cardiovascular system is mainly a laminar flow system, whereas the conducting airways of the respiratory system during inspiration and expiration are mainly a turbulent system. Now, one reason the respiratory airways are mainly a turbulent system is due to which of the following? One good answer is branching. They branch so often and so many times, it prevents the development of laminar flow. Now, a second variable here in the conducting airways is velocity. It's a very high velocity system, and that also promotes turbulence. So in the conducting airways then, because they branch so often and have a very high velocity, it is unlikely you're going to see very much laminar flow. Now, finally here, if you have a narrow orifice, a severe stenosis, it acts as a nozzle, and therefore that will also promote turbulence. If you have a very narrow opening with a high velocity of fluid going through it, that develops eddies and will disrupt the layers. A good example is aortic stenosis. Aortic stenosis will produce a very narrow opening, very high velocity through that narrow opening, and that will promote turbulence. Now, those are the important factors that determine laminar versus turbulent flow then. Now, the next topic here is to discuss series versus parallel circuits. Step one is very big on you understanding the consequences of connecting structures in series versus connecting structures in parallel. Now, the figure on this page here shows three theoretical resistors all connected in series. Now, when structures are connected end to end, they are connected in series. So this resistor, the second resistor, and the third resistor, because they're connected end to end, they are connected in series. Now, the very big initial point here is that when structures are connected in series, as stated on the slide here, flow must be equal at all points in a series system. So going to the model here, if I told you the flow through R3 was 10 mils per minute, you have to accept that the flow through R2 is also 10 mils per minute, and the flow through R1 will likewise be 10 mils per minute. The flow is the same at all points in the series system. Also, if we change some parameter in the system and the flow through R3 goes from 10 mils per minute to 13 mils per minute, you have to accept that the flow through R1 would also go from 10 mils to 13 mils per minute. So the bottom line point is, if you know the flow at any point in a series system, you know the flow at all points in that series system. A second characteristic of a series system is that the total resistance of the system is the sum of the individual resistances. If we go to the next slide here, this just shows the formula for calculating the total resistance in a series system. For the one we just looked at then, the total resistance is the resistance in R1 plus the resistance in R2 plus the resistance in R3. Now, this formula has certain consequences. Now, do not memorize these statements. They just should make sense as you go through here. First of all, based upon this formula, you should realize the total resistance in a series system is always greater than any of the individual resistances. The second point is, if you add a resistor in series, it will increase the total resistance of the system. And finally, when you connect resistors in series, it results in a high resistance system. So if I just had one resistor here, the total resistance is whatever the resistance is in this factor. If I add another resistor, I increase the resistance of the system. If I add a third resistor, the total resistance gets even higher. Now, you also have to understand some consequences, and this is the most important information here. You must understand consequences if you change the resistance in the center part of a series system. So what we're going to look at will be changing the resistance in R2. And we have to be concerned with what happens immediately downstream from this resistor and immediately upstream from this resistor. The first example we'll take a look at is the consequence of decreasing this resistance right here. If you decrease this resistor then, if you decrease the resistance here, then the total flow in the system has to go up. So upstream, the flow will increase. Downstream, the flow will increase. And the flow has to be the same at all points in the series system. Now, more importantly is the following. If I decrease the resistance here, what you have to understand is you lose less pressure going through the system, and therefore downstream the pressure increases. So downstream you have greater flow and greater pressure. Now upstream, we already said you have greater flow, but you will lose a small amount of pressure, so pressure will decrease. So upstream, you get an increase in flow, but you will get a slight decrease in pressure. Now, if we look at the opposite maneuver, instead of dilating or decreasing the resistance here, suppose we increase the resistance. Suppose this is a vessel and we constrict this individual vessel. Now, if we constrict here, then we have increased the total resistance of our system. Therefore, the flow through the system, the entire system, will decrease. Therefore, flow downstream will decrease and flow upstream will decrease. Now, the more difficult parameter to deal with, again, is pressure. If I constrict here, then, I have a higher resistance at this point. I lose more pressure, so downstream, the pressure will decrease. So downstream, I get a decrease in pressure, I get a decrease in flow, but upstream, even though flow goes down, immediately upstream, the pressure increases. So just to summarize this, suppose this is a single vessel in a hemodynamic system. If I dilate that vessel and decrease the resistance, downstream, I get more flow and more pressure. Upstream, immediately upstream, I will get more flow, but I will get a slight decrease in pressure. On the other hand, again, if this is a single vessel in a hemodynamic system, if I constrict this vessel, then, downstream, I get decreased pressure, decreased flow. Upstream, I will still get a decrease in flow, but I will get a slight increase in pressure. Now, applying this model to the entire systemic circuit, the entire systemic circuit can be considered a series system. The arteries are in series with the arterioles, which are in series with the capillaries, which are in series with the veins. Now, when we change resistance in the systemic circuit, we're changing the resistance of the arterioles. So just imagine that resistor 2 here represents the entire arterioles in the systemic circuit. And upstream here, then, we have the major arteries, and downstream, then, we have the capillaries. So this is the entire systemic circuit. And suppose we vasodilate the arterioles in general. If you vasodilate the arterioles, then, the flow through the systemic circuit will increase. Now, downstream from the arterioles in the capillaries, the flow will increase. So downstream, you'll get an increase in flow. Upstream, you'll also get an increase in flow. Now, again, the more difficult parameter is pressure. If I dilate here, then, downstream in the capillaries, pressure increases. But upstream in the major arteries, pressure decreases. In other words, if I give a drug that causes a major vasodilation of the arterioles, I will increase flow in the systemic circuit. Downstream in the capillaries, my pressure will go up. But upstream in the arteries, my pressure goes down. Now, looking at the other situation then, suppose instead of dilating the arterioles, we constrict the arterioles. If you constrict the arterioles, then, the flow through the entire systemic circuit should go down. Now, because you constrict right here, then pressure downstream would go down in the capillaries, but pressure upstream would go up in the arteries. In other words, if you give a drug that causes a major vasoconstriction of the systemic circuit, the flow goes down, capillary pressure also goes down, but arterial pressure increases. We can also relate this situation to an individual who tends to have essential hypertension due to overconstriction of the arterioles. If you have hypertension due to an overconstriction of the arterioles, the upstream pressure in the arteries goes up and the person is hypertensive, but you should understand downstream from the arterioles in the capillaries, the pressure actually goes down. A person who has essential hypertension may have a high blood pressure, a high pressure in the arteries, but that person will have a low pressure generally in their capillaries then. And that is just applying the characteristics of resistors connected in series. Now, in addition, you also have to understand the consequences of connecting structures in parallel. Now, on this slide here, we have a figure of the entire systemic circuit. And what we're trying to show here is that individual organs in the systemic circuit are connected in parallel. For example, the kidneys are connected in parallel with the skin, with muscle, and with bone. When structures are connected side by side, they are connected in parallel then. So the major organs of the systemic circuit are connected in parallel. Now, if you want to calculate the total resistance of structures connected in parallel, you have to use a different formula. Now, do not memorize this formula because it will not be required for questions in step one, but I want to use this formula to draw a conclusion about when you connect structures in parallel. Suppose we have several circuits connected in parallel, and the resistance of each one then is 0.5. Then the total resistance here will be a number a lot less than 0.5. So the total resistance here is going to be less than any of the individual resistances. Now again, you just have to accept that these are the consequences of connecting structures in parallel. When resistors or structures are connected in parallel, then the total resistance is a very small number. You have a very low resistance system. Also, the total resistance when structures are connected in parallel is always less than any of the individual resistances. And finally here, adding a resistor in parallel lowers the resistance of the system. Now, going back to the model here, if I add a structure connected in parallel, then I decrease the resistance of the system. For example, if a person becomes obese, if you put on a lot of fat tissue, what you're adding will be circuits connected in parallel. And therefore, theoretically, an obese person should have a lower total peripheral resistance than a non-obese individual. When you add circuits in parallel, then you decrease the total resistance of the system. On the other hand, if you remove a circuit connected in parallel, that will increase the resistance of the system. And a good example here is a fetus that at delivery. A good example is a fetus at delivery. Now, the placental circuit is connected in parallel with the systemic circuit. And therefore, at delivery, because you lose the placental circuit, a circuit connected in parallel, you increase the resistance of the system. So at delivery, the total resistance of the systemic circuit increases. Now, the other characteristic that is very important about connecting structures in parallel is that when they're connected in parallel, the flows can be independently regulated. Now, when they're connected in series, we said earlier, there is no independence. There is total dependence in a series system. In a parallel system, the flows can be controlled independently. Just because you have a change in flow in one parallel circuit doesn't mean you necessarily have to have a change in flow in another parallel circuit. For example, suppose you dilate the arterioles in the kidney. The flow through the kidney will increase. But if your blood pressure does not change dramatically, then the flow through the other parallel circuits should not change. As long as the perfusing pressure does not change, the flow in any parallel circuit should not change. Now, another point here that will extend on the next couple of slides here is the fact that parallel circuits have the same perfusing pressure. And if you have a general idea of the flow going through a structure connected in parallel with others, you can get a good handle on the resistance of that structure compared to the others. For example, if two structures have the same perfusing pressure, the structure with a higher flow must have an overall lower resistance. So perfusing pressures are the same. You can get a good estimate, a relative estimate of resistances by simply thinking about flow. The higher the flow to organs connected in parallel, the lower the resistance of that single structure. Now, there's a couple of logical questions they could ask based upon that point. Now, this is a very simple question right here, and it's all based on flow. The question is, which of the following circuits represents the lowest resistance pathway? Now, no one memorizes the resistances of individual pathways, but you should realize these are three pathways connected in parallel, and they have the same perfusing pressure. Therefore, the one that has the greatest flow will be the lowest resistance pathway. And that, of course, is the renal circulation. Now, the renal circulation gets about 20 to 25% of cardiac output. Because it gives such a large percentage of cardiac output, it must be a fairly low resistance circuit then. So the renal circuit is considered a fairly low resistance circuit because it has a fairly high flow. Now, suppose we change this question and instead ask which of the following circuits here is the highest resistance pathway. Now, the reasoning should be the circuit with the lowest flow should have the highest resistance. Now, of these three here, the least flow goes through the coronary circulation. Now, you don't have to know exact numbers at all, but the coronary circulation gets about 5% of cardiac output. That's a smaller percentage than the other two here, and because of that, that would represent a much higher resistance system than the other two. So it's all based on flow. Now, another question that is more likely for step one would be the following. Now we're simply asking the same original question. Which of the following circuits represents the lowest resistance pathway? You have 5 to choose from, and it is simply based on total flow going through that circuit. Now, the best answer here is the pulmonary circulation. It is the best answer because it has the highest flow of the circuits listed here. The flow through the pulmonary circuit is basically 100% of cardiac output. And an important point is the pulmonary circuit is considered a very high flow circuit. Because it is a high flow circuit, It means it must be a fairly low resistance system. Now, just to add an additional detail here, the pulmonary circuit, as you know, is also considered to be a low pressure circuit. Now, just thinking logically, if you have a high flow that is pushed through with a low perfusing pressure, it must be a very low resistance pathway. Therefore, the pulmonary circuit is characterized as a high flow, low pressure circuit. And that must mean it's an extremely low resistance pathway. It has much lower resistance than the entire systemic circuit. Now, there is a hemodynamic model that they could throw at you to test your understanding of hemodynamics, at least the properties we've gone through so far. Now, this is just an example of one simple hemodynamic model that you could be expected to interpret on the exam. Now, this is not real high yield, but they have put these simple models on before to see if you understand the basic principles of hemodynamics. Now, the first point I want to emphasize here is that this is not the systemic circuit. The systemic circuit is a branching circuit, and therefore you cannot apply the characteristics you've learned about the systemic circuit necessarily to this model. This model represents 3 individual vessels all connected in series. It is not a branching circuit. It is simply 3 tubes connected in series. Now, going through these questions one at a time, you have answers on your handout here, but it's important to understand why a particular answer is correct. First of all, how does flow compare in regions A, B, and C? Because these are 3 tubes connected in series, the flow must be the same at all points in a series system. Therefore, the flow in A, B, and C is the same. And don't forget, this is not velocity. This is flow in mils per minute. Now, the second question is, which section has the greatest wall tension? Now, the greatest wall tension will be in a large vessel that has a large diameter. Therefore, then, the best answer is A, then. A has the greatest wall tension. Now, number 3 here, which section has the greatest velocity? Now, this is speed. And I said earlier that velocity is always inversely related to cross-sectional area. Therefore, because C has the smallest cross-sectional area, it must have the highest velocity. And velocity is speed measured in centimeters per second. The velocity in A will be much less than in C because it has a greater cross-sectional area. Now, number 4 asks, which section has the greatest resistance? Now, because it is 3 tubes connected in series, because C has the smallest radius, then, it must have the greatest resistance. And finally here, which section has the greatest pressure loss? Now remember, you lose pressure overcoming resistance. Therefore, because section C has the greatest resistance, you lose most of your pressure going through section C. Now, just to illustrate this with more detail to complete our understanding here, you start, we'll say, at the beginning with a pressure of 100 millimeters of mercury. Now, you're going to lose that pressure overcoming resistance. Now, as you pass through section A here then, because this is a low resistance component, you lose very little pressure. So the end of component A, or section A, the pressure may have only dropped from 100 millimeters of mercury down to 95. Now, as you go through section B then, you have a section with greater resistance, therefore you lose more pressure. So the pressure here may go from 95 down to 60. So you lose more pressure going through section B. Now, because section C has the greatest resistance, you lose more pressure here. Therefore, the pressure at the beginning of C may start at 60, but you'll probably lose the entire 60 going through C. You'll lose most of your pressure in C because it is simply a higher resistance component. Now, that represents a generalized model of the systemic circuit. Now, we're going to continue by talking about some other general characteristics of the systemic circuit or any hemodynamic system. And the next topic here is wall tension. Now, you have to have a general idea of what creates wall tension. Now, you don't have to have an exact idea about what wall tension actually is. I simply think of wall tension as a force that develops in the vessel wall. It's simply a force in the vessel wall that tends to split that wall open. So the higher the wall tension, the greater the force in that wall that tends to disrupt the structure of that wall. Now, the relationship between wall tension and the pressure in the vessel is given by the Laplace relationship. Now, these are the important points here. In a blood vessel, we'll say this is an artery. It is the pressure in the artery that creates the wall tension. And the higher the pressure in this artery, then, the greater the wall tension will be. But the actual magnitude of the wall tension not only depends upon the pressure in the vessel, but on the radius of the vessel. And people quite often simply memorize that wall tension is the pressure in the vessel times the radius of the vessel. Now, the important implication here is, if you have an artery, and we'll say the pressure is constant throughout this artery, we'll say at 100 millimeters of mercury. If you have an aneurysm that develops in an artery, the pressure in the artery generally does not change. However, as the aneurysm develops, then, the radius of the vessel increases. And because the radius increases, then, wall tension increases. The bottom line point is, as an aneurysm develops, because the radius is increasing, wall tension increases, and that vessel is more likely to burst. For some reason, some people seem to think if a vessel enlarges, you're actually relieving wall tension. That is not the case. The wall tension always increases and the vessel is more likely to burst. Now, on step one, they could also ask you then an extension of this. And a good question would be, which vessel in the entire systemic circuit has the greatest wall tension? And the best answer would be the aorta, for two reasons. It's a high-pressure vessel with a large radius. So because it is a high-pressure vessel with a large radius, it has a very large wall tension. Therefore, then, the aorta must have a very strong wall to avoid or to counteract, the aorta must have a very strong wall then to deal with the high wall tensions. Now, taking the other extreme, suppose we go to a capillary. You should realize that capillaries have extremely low wall tensions. They have low wall tensions because the radius is so small. So even though a capillary may have a pressure of, we'll say, 40 millimeters of mercury, it does not create much wall tension, so there does not need to be much strength in a capillary wall. So just to repeat the main point in capillaries, because the radius is so small, the wall tension in capillaries is also very small. So capillary walls do not need to have much strength because they have very little wall tension to deal with. Now that represents the important applications of wall tension. The next topic I want to briefly start on here is vessel compliance. Now you can calculate the compliance of a vessel by using this formula here. By definition, compliance is the change in volume within the vessel divided by the change in pressure. But the number you calculate for an individual vessel is basically meaningless. And because the number is meaningless, you will never have to deal with a calculation of a vessel's compliance. Instead, you simply have to understand the concept of compliance here. And this is a good general definition of compliance. You can simply think of compliance as essentially how easily a vessel is stretched. If a vessel is easily stretched, it is considered to be a very compliant vessel. So if a vessel is very easily stretched further open, it is considered a very compliant vessel. The opposite would be non-compliant or stiff. A stiff vessel is a very non-compliant vessel. Now, as we go through the remainder of this material, if you just have that general concept of compliance, there should be no problem whatsoever. Now, continuing on with the characteristics of the systemic circuit. This figure shows a general pressure pulse recorded from a systemic artery. Now, just to go through the basic characteristics of this pressure pulse. In the aorta, we'll say, the peak pressure here is called your systolic pressure, and in the aorta, it's about 120 millimeters of mercury. The low pressure is called your diastolic pressure, and again, in the aorta, under normal conditions, it is about 80 millimeters of mercury. Now, mean pressure is the average pressure in the artery. But you should realize that mean pressure, for some reason, is closer to diastolic than it is to systolic. So what you have to remember is that mean arterial pressure is the average pressure in the arteries. But for some reason, it is closer to diastolic pressure than it is to systolic pressure. Now, another parameter here, and it's the derived parameter, is pulse pressure. Now, we'll talk about this further on here, but pulse pressure is simply the systolic blood pressure minus the diastolic pressure. Pulse pressure is simply the difference between systolic and diastolic pressure. Now, looking at how specific parameters can change here, you should have a general idea of what can change systolic pressure, or the peak pressure reached during systole. Now, what we've shown here are the factors that will increase arterial systolic pressure. But of course, the opposite changes would decrease arterial systolic pressure. Now, there's only three that are reasonably important here. If you increase stroke volume, that will tend to increase systolic pressure. Now, this should make sense. If you're pumping more blood into the aorta, it would cause a greater rise in pressure, and therefore systolic pressure should increase. Now, another parameter which is very important to accept here is that systolic pressure will increase if you decrease vessel compliance. Therefore, then, systolic pressure increases if a vessel is a stiff vessel. If you pump blood into a stiff vessel, then there is less stretch of the vessel wall, and therefore the peak pressure will increase then. And that is an important point to remember. Finally here, if you decrease heart rate, you will get an increase in stroke volume, and this is just basically a repeat of the first variable. So the bottom line simply is, if you pump more blood into the aorta, systolic pressure goes up. If the aorta becomes stiffer, or if an artery becomes stiffer, systolic pressure will also increase. Those are the only two important parameters that affect systolic pressure. Now, if we consider diastolic pressure, which is the lowest pressure that you attain at the end of arterial diastole, now the following here, the ones listed here, will decrease arterial diastolic pressure. But you should also realize the opposite would tend to increase arterial diastolic pressure. Now, the first one here is the most important. If you decrease total peripheral resistance, that will decrease diastolic pressure. Now, this should make sense. If you vasodilate and you decrease total peripheral resistance, then more blood will flow through those arterioles then, and therefore there's less volume in the systemic arteries, and your blood pressure would decrease. It is very important to know that if you cause a vasodilation, then diastolic pressure will decrease. Now, the second parameter, not quite as important, if you decrease heart rate, then that will also decrease aortic diastolic pressure because you have more time available for the blood to empty from the arteries. So if heart rate goes down, there's more time to empty the arteries then to peripheral structures, and therefore arterial diastolic pressure would also go down. And finally, if you have a decrease in stroke volume, you are pumping less blood into the systemic arteries, and therefore then the diastolic pressure would also go down. And again, those are the only important parameters you have to deal with that will affect diastolic pressure. Now, the final parameter here is pulse pressure. Now, people have more difficulty dealing with pulse pressure. Remember, it's simply the difference between systolic and diastolic pressure. So putting it into a formula then, pulse pressure is your systolic minus your diastolic pressure. If we use normal values here, a normal value for systolic pressure is 120. A normal diastolic pressure is 80. Therefore, a normal pulse pressure would be 40 millimeters of mercury. The way I look at it is pulse pressure is simply the distance between these two numbers. If the numbers get further apart, pulse pressure increases. If the numbers get closer together, your pulse pressure decreases. Now again, we put specific parameters here that can change pulse pressure. We organized it here such that the following will increase pulse pressure. So the numbers will get further apart. And these two parameters here you should understand as increasing pulse pressure. For example, if you have an increase in stroke volume, just accept that systolic pressure increases more than diastolic pressure. Therefore, then, you should realize the numbers will get further apart and pulse pressure will increase. On the other hand, suppose you have a decrease in vessel compliance. If you have a stiffer vessel, then you will have a systolic pressure that increases and a diastolic pressure that decreases. It is very important to understand and accept that if a vessel becomes stiffer, you will have an increase in pulse pressure. So just to summarize that then, because it is an important point. If you have a stiff vessel, you will have a large pulse pressure. On the other hand, if you have a very compliant vessel, you will have a smaller pulse pressure then. Very important point to remember. Now, one way they could test this on step 1 is to throw at you a couple of pressure pulses. And they could ask you to pick out which of these pressure pulses would best represent, and they're not drawn perfectly here, but they could ask which would best represent the aorta and which best represents the femoral artery. Now, it's all based on pulse pressure being related to compliance. Now, pulse pressure is your systolic minus your diastolic. So for the first one here, then, it would be this pressure, whatever it is, minus this pressure down here. Or, same thing would be this pressure right here. Now, if you look at the second pressure pulse here, this would be the systolic pressure here, and this would be the diastolic pressure right here, or you could possibly use this point right here. Now, this should be your reasoning. If you have a very compliant vessel, you should have a smaller pulse pressure. So this vessel here is more compliant than this vessel here. This vessel is more compliant because it has a smaller pulse pressure. This vessel is stiffer. This vessel is stiffer because it has a larger pulse pressure. Therefore, then, the first figure best represents the aorta because the aorta is considered an elastic artery. It's a very compliant artery. Whereas the second one here would be the best answer for a peripheral artery, such as the femoral artery. Peripheral arteries are more muscular, therefore they are stiffer arteries. And as I said, it is important to understand the relationship between compliance and pulse pressure. Now, the next topic I want to go into, and we're just going to be adding a couple of more details here, and that is mean pressure. Now, we already mentioned that mean pressure is the average pressure. So mean pressure in the aorta is the average pressure in the aorta during a single cardiac cycle. We also showed in a previous figure that this pressure is closer to diastolic pressure than it is to systolic pressure. And the important implication of that is that diastolic then is a better index of mean pressure than is systolic pressure. It is important to remember that because diastolic pressure then is closer to mean pressure than is systolic, diastolic is a better index of mean pressure. Also, you can roughly calculate a value for mean pressure using systolic and diastolic pressures. Now, on step 1, they could give you 5 formulas and ask you which of the 5 formulas is the best for estimating mean pressure. Every formula is just an estimate. Now, all you have to remember is the number you calculate has to be a number that is slightly greater than diastolic pressure. It must be slightly greater than diastolic. It must be closer to diastolic than systolic. So that is your basis for picking the best answer here. Now we put in two formulas here. This is the easier one to deal with. Mean pressure can be calculated as diastolic plus 1/3 pulse pressure. Now that gives you a number that is slightly above diastolic. It is closer to diastolic than it is to systolic, so that would be a reasonable formula then for calculating mean pressure. Now another one that is equally correct but more difficult to analyze is that mean pressure is 2/3 of diastolic pressure plus 1/3 of systolic pressure. Now if you just plug some normal values in here, you will come out with a number again that is slightly above diastolic. So that is your focus in terms of picking up the best answer here. Now we also have to consider another application of the Poiseuille equation. And it is this application that is most important for step 1. Now all we're doing with the information on this page is we are relabeling that original Poiseuille equation that simply said flow is equal to P1 minus P2 divided by resistance. Now what we're doing here is we're just applying that equation to the entire systemic circuit. Now just follow me through on the reasoning here. Instead of flow, we're putting in cardiac output because that is the flow through the systemic circuit. Now P1 is the pressure at the beginning of the system, and that of course is mean arterial pressure, but technically it should be mean aortic pressure. But don't forget there's very little pressure change as you go through the major arteries, so this represents the pressure in any major artery. Now this is the detail that makes this a little bit more complex. Technically, we should subtract the P2 downstream. Now P2 is the pressure at the end of the system. At the end of the systemic circuit, you have the right atrium. Therefore, we should actually subtract from mean arterial pressure right atrial pressure. But because right atrial pressure is fairly low and constant, we just eliminate that number to make the equation simpler to deal with. Therefore, even though P2 is right atrial pressure, we're eliminating it because it's a small number and it does not change dramatically. Now the third variable in the Poiseuille equation is resistance. We have to divide by the entire resistance of the systemic circuit. Now the entire resistance of the systemic circuit is referred to as total peripheral resistance. By definition, total peripheral resistance is the resistance of the entire systemic circuit. But we mentioned earlier, most of the resistance of the systemic circuit is in the arterioles. Therefore, even though TPR, total peripheral resistance, represents the resistance of the entire systemic circuit, for all practical purposes, TPR is the resistance of the arterioles. And when you're changing total peripheral resistance, you can always assume you're simply changing the resistance of the arterioles. Now, when the equation is in this format, it is not too useful. It is much more useful if we change it to this format right here. Now, this equation is extremely important to understand. It is very useful for a large number of questions on step 1. Now, all this question basically states is that mean arterial blood pressure, which is kept close to 100 millimeters of mercury, your blood pressure is only determined by two variables. One variable is cardiac output. The second variable is total peripheral resistance. These are the only two variables then that affect mean arterial pressure. Now, we already said that TPR is determined mainly by the resistance of the arterioles. So one of the two variables that determines your blood pressure is simply the resistance of the arterioles. If you increase the resistance of the arterioles, blood pressure goes up. If you decrease the resistance of the arterioles, blood pressure would go down. Now, the other variable is cardiac output. Now, what I usually tell people here is, do not think specifically cardiac output. It is better to think instead circulating blood volume. So instead of thinking cardiac output, think more abstractly here. You think circulating blood volume. And the point is, the blood that is stored in the systemic veins is not contributing to cardiac output. So cardiac output is circulating blood volume. It does not include the blood stored in your reservoirs. Now, looking at examples here to illustrate how this equation is very useful, one situation is simple hemorrhage. Now, if we examine exactly what goes on in a hemorrhage, first point, what do you lose in a simple hemorrhage? If you hemorrhage, what you lose is cardiac output. And therefore, if you lose cardiac output, mean arterial pressure decreases. Now, if nothing else happens, you would have a significant drop in mean arterial pressure. Now, the body does not want to lose all of that pressure, so what does it do? It increases total peripheral resistance. The increase in resistance then compensates for the loss of cardiac output. Now, this would be a good question for step one. A patient comes into the emergency room, and this patient has had a slow but progressive hemorrhage. However, when you measure that patient's blood pressure, it is still in the normal range. How can you explain a normal blood pressure in a patient with a slow but progressive hemorrhage? And the answer has to be what? An increase in TPR. The increased TPR prevented a decrease in pressure. Now, with that question, what they're actually testing here is that blood pressure, the measurement of a blood pressure in a patient who is hemorrhaged, is not a good index of the volume of blood lost in that hemorrhage. So the measurement of blood pressure then is not a good index of the volume lost during the hemorrhage, because TPR can almost completely compensate under certain conditions.